All right, from now on, we're going to talk about transfer learning. You want to train your own CNN. However, if you need very large scale data set, then how would you tackle that issue? That is the topic of transfer learning. This is the architecture of AlexNet. And when we visualize the filters at the early stage, this is the input, and this is the output, class scores. And the early stage filters looks like this. And as you can see here, it's about edges, and very low level features. And when we visualize features at the top level, it looks like this. As you can see here, it contains more of semantic features rather than generic features. So the early stages entail generic features, and the later stages entail semantic features. And what does it mean by transfer learning? In usual and generally, when we want to develop our own CNN for our own application, we do not have a large scale data set. However, ImageNet is a quite large data set. In that case, we first train our CNN on ImageNet, which is a large scale data set. And then if our data set contains C classes, we just freeze these parts and only replace the fully connected layer at the top. This one is for classifying 1000 classes. However, for our application, which contains C classes, we just need fully connected layer for C classes. We just replace this fully connected layer, reinitialize, and train. This process is sometimes called fine-tuning. And we do not modify the weights in these stages. And fine-tuning sometimes shows better performance. In this case, these two models are trained from scratch from the target dataset. And these two models are fine-tuned from AlexNet, which is pre-trained on ImageNet. Therefore, when you're developing your own application, start from ImageNet and then move on to your specific application. And if you have a little more bigger data set, then you can freeze less number of layers like this. And then you can train these 3 layers rather than just single layer like this. And if you have even bigger data set, then you can freeze only up to this point and you can retrain this part. And it depends on your application, and nobody knows how many layers to freeze. You need to find the optimal point by trial and error. And when you're fine-tuning, you better use low learning rate, usually 1/10 of the original learning rate. And this could be a good starting point. And when you have very little data and your data set is quite similar to that of ImageNet, then what should you do? And what if your data set is very different from ImageNet? And in another direction, what if you have quite a lot of data? And I told you that early stages entail more generic features, and upper layers contain more specific and semantic features. We saw this. In this case, we just replace the top convolution, fully connected layer for your application. And if you have a lot of data, then you just move a little deeper and fine tune more layers. However, if your data set is quite different from the ImageNet, for example, you want to classify stars or diseases. In these cases, the data sets are quite different from ImageNet, which contains cars or birds, plants, like this. In that case, it's quite hard to solve this problem. You may try linear classifier from different stages, like from this stage, because these entail more generic features. You want to start from here. And this becomes very hard to choose where to start. And when you have a large number of data set, then you can fine tune a large number of layers. And transfer learning with CNN is pervasive, meaning that it is the standard. It is not an exception. For example, object detection network and image caption network, they all used AlexNet, which is pre-trained on ImageNet. Not AlexNet, but CNN pre-trained on ImageNet. And this part is also pre-trained with Word2Vect. And we're going to talk about what Word2Vec is in the later of this course. Therefore, even though you have quite a lot of data set, that might be still smaller than ImageNet. Therefore, you might want to use bigger data sets first and then fine-tune those models pre-trained on bigger data sets on your specific application data set. And architecture also matters. So the object detection performance differs largely depending on the architecture, even though they are pre-trained on the same ImageNet. However, sometimes pre-training might not be always necessary. However, starting training from scratch might take more time, like 2 to 3 times longer. And sometimes collecting more data is better than fine-tuning. And there is no rule of thumb. You just need to try and find the best optimal position. And takeaway for your project and beyond is, if your data set is smaller than 1 million images, then find a very large data set that has similar data and train a big component there and transfer learn to your data set. And deep learning frameworks like PyTorch and TensorFlow already provide a model zoo, pre-trained models, so you don't need to train your own. And another good news is they provide the same architectures like ResNet 18, pre-trained on different datasets like ImageNet or MS Coco, like this, meaning that you have a variety of options. You better choose you better test different types of pre-trained networks and find the best option for your application. Okay, let's summarize this session. In the beginning, we introduced the motivation by speech recognition task. We wanted to find position invariant model and convolution was one of the best options to train position invariant model. And we talked about what convolution was, and we talked about filter number, stride, head, and different things. And we also talked about CNN architectures. Some architectures have their own motivations, and we can use those motivations to design our own architectures. And we also talked about transfer learning to develop your own applications. You don't have to start from the beginning. You can get pre-trained networks from the deep learning frameworks and use those pre-trained networks and enhance the performance of your own CNN model. All right, that's the end of this session.